All right, guys, in this module, it's going to be time for us to spend a significant amount of effort looking at the idea of our routing protocols. I want to begin with our IGP known as Eigrp, Enhanced Interior Gateway Routing Protocol, a Cisco proprietary protocol that has gone mainstream, but Cisco has utilized this protocol in a number of ways to be able to enhance the performance of our networks. And what I want to do is I want to look at that. Now, when we go in and we start operating with our dynamic routing protocols, it's important for us to understand that the reason that they exist is just like they were as we discussed in ICND1. We have the discovery of remote networks that's going to be one of their primary responsibilities, and the fact that we're going to use them to communicate information to prevent us from having to use the static routes that we've been discussing in our previous studies. So when we go in and we start implementing something like Eigrp, we're finding ourselves recognizing the first value is that we have the idea of AD, administrative distance. I told you that it's going to be 90 for internal prefixes. It's also going to be 170 for external prefixes. AD corresponds to the believability of a particular prefix or a route that we're learning, the protocol itself. Now, when we start looking at this, what we need to recognize here is there are the possibility that we can learn about multiple prefixes via the same protocol. So in other words, administrative distance is only going to come into play when I have two different routing protocols learning prefixes. And then what I'm going to do is I'm going to pick the lowest. However, if I'm learning the same information from the same routing protocol, by default, I'm going to have the capacity to be able to load balance provided, or load share, provided that my metrics are the same, that they match. So what I want to do is I want to dive right in and let's do an Eigrp configuration in our topology. But first what I want to do is I want to illustrate what that topology looks like. So right now, what I have in my configuration is I have four devices, R1, R2, and R4. Now I'm going to draw this out such that I have R1 connected to R2, connected to R3, connected to R4. We're connected with individual connections. There are going to be gigabit connections that are going to be across our configuration, and what we want to do is exactly explore what all of those are. So when we look at this, the fastest way to find out what our addresses are is going to be show IP interface brief. This is going to give me my list of interfaces, and notice I'm using 00 and 01, 02, and 03 in this scenario. So here's the way the system is actually connected. What I'll do is I'll come up here and I'll grab my black pen. I'm going to say 00, 00, 00, 00, 00, and it's going to be 01 connecting the verticals. Now this is going to be my interaction. Now I also have some configured loopbacks. My loopbacks are going to be 2.2.2, 4.4.4.4, 1.1.1.1, and 3.3.3.3. So what we're going to do is we're going to advertise those loopbacks, and we're going to create a situation whereby we build all of our Eigrp neighbors and we bring our network up and make it operational. So let's take a look at exactly what's involved in that process. So from the point of view of the router, what I need to do is I'm going to say config T, and I'm going to say router Eigrp, and I'm going to give it an autonomous system number. I'm going to say 10. Because I'm old school, and a lot of the routers that I work on are not as modern or as new as some of the ones that I have here in my illustration, I'm going to say no auto summarization, because Eigrp is going to summarize at the classful boundaries automatically. In modern iOSs, the ISR2 values and stuff, the system doesn't do that. Now what I'm going to do is I'm going to specify that I want to advertise a network. I want to advertise, first of all, my loopback. I'm going to say 0000. I'm going to match it exactly. So I'm going to advertise 1.1.1.1. I'm going to run OSPF on that interface. Now the moment I do this, I can type do show IP protocols. And what I can see here is what interfaces are now going to be participating. Notice right here, I'm actually running it for the network 1.1.1/32. Another way that I could see this would be to do show IP Eigrp interfaces, and it's going to tell me what interfaces are participating in Eigrp. Now, what I want to do is I want to form a neighbor relationship between all of my devices so that I have everything up and running. Now, in order to be able to do that, I'm going to do a shorthand. So what I want to do with one command, I want to actually have E00 and E01 participate in EIGRP. The way that I would do that is I'd say network, and I'm going to say 10.100, and I'm going to say anything that matches 10.1. I don't care what's in the third octet. I don't care what's in the second octet, or the fourth octet, excuse me. I want those to participate in EIGRP. I can verify that, again, with that single show command, show IP interface, or show IP EIGRP interface. Now I see Ethernet 0, 1, and 00 are participating in EIGRP. Let's go through and do the rest of the configuration on R2, R3, and R4. So a config T, router, EIGRP 10, network, I want to advertise 2.2.2 exactly. And I want to do, again, that network where I'm advertising the /16. So it's going to be 10.100.00.255.255. I hit enter, and I should almost immediately see a neighbor adjacency form. So I've formed a neighbor relationship with R1. It's telling me R1 because I know that's the IP address of R1 on this segment. Now, do show IP EIGRP interfaces, and I'm going to see I'm actually running it on both my interfaces, my Ethernet interfaces, and my loopback. So let's repeat this process on 3 and on 4. So config T, router EIGRP 10. I'm going to say network 10.1.0.0.00255.255, and network 3.3.3. Specifically, I want to participate in the EIGRP. And again, I see my neighbor come up. So over here, let's do the final configuration on R4. So it's going to be config T, router EIGRP 10, network 10.1.0.0.00255.255, and network 4.4.4.4 match exactly. So now what I'm going to end up having here is between R4, R3, R2, and R1, I have peering relationships. Let's explore those. Show IP EIGRP neighbors is going to tell me that I should be connected to R3 and R2. Over on R1, if I do the same thing, I should be connected to R2 and to R4. And show, actually it'll be R3. So show IP EIGRP neighbors. And notice I'm connected to R3 and R2. So this device is connected here and connected here. Now what I want to do is I want to look at my routes that I'm learning. Let's look at the nature of those routes. I'm going to do that by typing show IP route, but I only want to work at EIGRP prefixes. And what we're going to see here is that we've got quite a few routes. In fact, we have 4 routes. We're not learning our locally connected route because it's locally connected, and that's going to have a better administrative distance than the idea of 90, which is going to be what we're learning from EIGRP. Now let's look at this. What I'm looking at right now is 4. Notice 4 has 2 prefixes. It has 2 prefixes because these prefixes have exactly matching metrics. That tells me that I'm going to try to load share if I try to send information to that destination. I can verify that by typing traceroute 4.4.4.4 and hit enter. And what we're going to see is the system is going to pick multiple paths to reach a destination, R2 and R3. So we're going to try to load share when and where possible across those particular links. Now the other part of this is that I can actually do a trace route to say 3.3.3.3. And what we're going to see is it's only going to pick one path because it's going to pick the closest or the shortest path to reach its destinations. Now, what we've just illustrated here is going to be some of the key benefits to EIGRP. And let's look at those. EIGRP is as popular as it is because of the fact that it converges so quickly. So it has very rapid convergence. Remember, when we're converging, we're not forwarding data. EIGRP supports load sharing. EIGRP utilizes the dual algorithm, the diffusing updating algorithm, that's going to allow me to create a loop-free topology, and is also going to support the idea of variable link subnet masks. Why? Because it is a classless routing protocol. So it ignores the idea of Class A, Class B, and Class C so long as the no summary configuration is turned off. The other thing here is it gives us the capability of reducing bandwidth usage. So in other words, we can bound updates using the concept of a stub area, and we can also eliminate the requirement of things like broadcasts that we would be sending, say for instance in RIP, based on its normal operation. So we can see there's a lot of direct benefit to using a routing protocol like EIGRP. Now, the other part of this is we need to understand this path selection process. So how does EIGRP pick a path? So what is a best path? Well, best path is actually going to be based on a metric. And in the confines of that metric, when we start looking at it, by default, what we're going to end up finding here is that we're going to first understand what's going on, or we need to look at it. So if I had a scenario where I had a router connected to another router, and I have a loopback interface or a network connected here. Let's say it's 10.1.1.0/24. Now, this is going to have a metric value. Let's say it has 1,000. Let's say the link between these two routers is also 1,000. Well, what's going to end up happening here is from the point of view of this router, it's going to take 1,000, add it to 1,000, and it's going to say I have a metric to reach this network of 2,000. The lowest value is going to be the value that we're going to want to employ or we're going to want to use. And the only time metric really becomes important to us is when we have multiple paths like we have right here, because the metric must match identically to do equal cost load sharing. Now, the other part of this is like I said, in the very first part of ICND 1, when I was talking about the routing protocols, I mentioned that a lot of people try to pitch EIGRP as if it is going to be a hybrid routing protocol, like it's got a foot in the link state world and a foot in the data in the distance vector world. And that's not the case. However, it does have some optimizations and benefits that don't exist in other distance vector routing protocols. One of them is the fact that it has a topology table. So show IP EIGRP topology table. And what I'm going to see here is I'm going to see every prefix that I have in my system that I'm learning. Not all of these are going to be placed in my routing table necessarily, but what we also need to recognize here is that where we have load sharing, we have the specific values that, i.e. our prefixes are going to be matching. Not our prefixes, but our metrics. So again, keep in mind that we determine cost based on this metric value. Now, when we go through, how do we calculate that metric value in EIGRP? In the confines of EIGRP, our metric is computed based on a value of bandwidth and a value of delay in combination. So when we go in and we start looking at this, we can also turn on other features. We could turn on reliability if we wanted to. Cisco says leave it alone. We could turn on load calculations based on the load of a circuit. Cisco says leave both of these alone. Unless you're specifically instructed to do so, never manipulate or alter the configuration of how the EIGRP metric is going to be calculated. So again, when we start looking at this, let's pick an interface and say we want to look at the confines or how that interface is configured. I can execute the show interface, and let's say I want to use E00 and I want to look at this. Well, what the information I'm looking at here is the MTU. That's the maximum transmittable unit. But the area I want to focus on here is going to be bandwidth. Notice I have bandwidth measured in kilobits per second and delay that's listed here in thousands of microseconds. Well, it's going to be microseconds itself. So the main thing that we need to recognize here, this is where all of that information is, to include issues of reliability and even receive and transmit load when it comes to whether or not we want to be able to incorporate those into our best path calculation process. Now, we've already walked through how best to advertise prefixes. I'm a big fan of using inverse masks. So I'll cite the actual address that I want to advertise, and I'll have the most accurate, specific, detailed mask I can, inverse mask, normally all zeros, because I want to be very, very selective as to which interfaces I advertise or which interfaces I say are going to participate in EIGRP. Now, if I don't do that, sometimes I can run into problems as I start adding interfaces. So if I get really gregarious with regard to how I'm advertising prefixes, when I add a loopback, sometime you may accidentally, or add another network, you may accidentally start advertising it into your infrastructure. That could definitely happen in this scenario where it did that 10.1.0.0 space 0.0255255. So what we may want to do is we want to make certain that we're doing this as specifically as possible in order to ensure that we don't accidentally cause ourselves problems. Now, another scenario or another command that I really think it's important for us to look at is the show IP Eigrp neighbors command. The show IP Eigrp neighbor command is going to be very important to us because it's going to tell us which addresses we're forming relationships with. It's going to tell us what interfaces we form them on, but it's also going to give us this value here called the queue count. If you have a queue count that is anything other than 0, be advised that you have a problem in your Eigrp topology. And it's definitely going to be something that you're going to want to make certain that you address. Now, the thing is that when we look at this, keep in mind these values that we're employing here are going to be used for our neighbor adjacencies. What I want to do now is let's take a look at the show IP Eigrp topology table one more time. And what I want to illustrate here is the fact that we also have this value of autonomous system. So in order for me to perform a peering across a link, both of my devices have to be participating in the same autonomous system with Eigrp. So I can't have Eigrp router Eigrp 10 on one side and 20 on the other and expect those two devices to form a neighbor relationship. No, the autonomous system must agree. The other thing is that when we start looking at this, we also have an Eigrp router ID. Notice it took the IP address of the highest IP address of a loopback interface. We only have the one. I can actually come over here to R4 and do the same command, show IP Eigrp topology, and it's going to give me my Eigrp router ID for this particular interface also. Now, we've illustrated this whole idea of the topology table because what's going to happen here is the topology table is going to give us quite a bit of information because it's going to be the only protocol that we have that we're going to deal with that's going to maintain alternate or backup routes if a certain condition is met. That condition is called the feasibility condition. So in other words, if the distance a router reports to us as to how it's going to get to a particular destination, what it's going to cost it, what the actual metric is less than the feasible distance of our successor, the successor is going to be that best route that we have, we can actually have a backup route included in the Eigrp topology table. That backup route would immediately be placed in the routing table if we lose our best path route. So Eigrp does have the benefit over almost every other routing protocol that we have to work with in the fact that it's going to allow us to be able to not have to redo the computation, provided we have an idea of a feasible successor. We have a successor which is going to be the best route. We have a feasible successor which would be the next best route. But the only time the feasible successor is going to be able to be placed inside of the routing table is if we lose the successor route or that best route. Now, the other part of this is we also have to understand that Eigrp supports load sharing. Now, it does equal cost load sharing and it does unequal cost load sharing. Now, what's going to end up happening here is notice that we only would load share in scenarios where our metrics match. So our values are the same, so they're identical, so we're going to use them equal. Each one of these particular interfaces is going to have a particular load count. Let me illustrate that. What I'm going to do is I'm going to come over here and I'm going to show IP, actually we'll show IP route for 4.4, is it 4.4? No, it's on here it'll be 1.1.1.0. And what we're going to see here is we have all of the information that we saw before, but the thing I want you to see here is the traffic share count is going to be 1. So in other words, if we so chose, we're going to load balance across these links since they're identical using a 1-to-1 ratio. Now, that depends on whether or not it's going to be supported at layer 2 in the confines of things like our Cisco Express forwarding and stuff. But the main thing that we need to understand here is by default, the system is going to choose how to do that. But we need to do configuration here in the confines of setting up unequal cost load sharing. Now, if I wanted to be able to do unequal cost load sharing, first of all, I would have to have a successor and a feasible successor in my topology table. So it's impossible for me to do unequal load sharing, unequal cost load sharing, unless I have a feasible successor. And then what I can say is I can use a command called variance to say that I'm going to use a coefficient of anywhere from 1 to 128 to say if the metric is 1 to 128 times worse, still do load sharing across the link. It's very difficult to illustrate a scenario whereby all of that comes in, but the main goal here is the EIGRP is a very simple, straightforward protocol that's made available to us by Cisco because it is initially proprietary. It has recently, within the last 8 months, been released as a standards-based protocol, but EIGRP is a very, very handy tool with regard to creating configurations and being able to exchange these dynamic prefixes across our infrastructure. So with that being said, let's move on to the next lesson. I'll talk to you guys there. Bye-bye.